Section 1 Introduction. Let's dive into the world of large language models, LLMs, which have shown great promise in various natural language processing, NLP, applications. However, there's a hitch. These models have a tendency to hallucinate, meaning they generate content that strays from the facts they were trained on. This is a significant hurdle, especially in high-stakes areas like healthcare or law, where accuracy is paramount. Why do these models hallucinate? One theory points to the way they're trained. They're designed to minimize the difference between the data they're trained on and the data they generate. This can lead to models that assign some probability to sentences that don't align with the facts in the training data. In practice, this means the models often recognize patterns in the training examples, rather than understanding and generating real-world facts. From an interpretability perspective, transformer LLMs seem to encode basic information, like part-of-speech tags, in the early layers, and more complex, semantic information in the later layers. Recent studies have found that knowledge neurons are distributed in the top layers of pre-trained models like BERT. Some have even shown that factual knowledge can be edited by manipulating specific layers within a transformer LM. We propose to leverage this layered encoding of knowledge to enhance the factual accuracy of an LM. We suggest a contrastive decoding approach, where the probability of the next word is determined by the difference in outputs from a higher layer versus a lower layer. By emphasizing knowledge from higher layers and downplaying lower or intermediate layer knowledge, we aim to make LMs more factual and reduce hallucinations. To illustrate, consider a simple example where the model is asked to name the capital of Washington State. While Seattle maintains a high probability throughout all the layers because it's a plausible answer, the probability of the correct answer, Olympia, increases as the higher layers inject more factual knowledge. By contrasting the differences between the layers, we can reveal the correct answer. Based on this concept, we propose a new decoding method, decoding by contrasting layers, DoLa, to better surface factual knowledge embedded in an LLM. Our experiments show that DoLa can increase the truthfulness of the models, facilitate more factual reasoning, and generate more factual responses. Plus, it only causes a small additional delay in the decoding process, making it a practical strategy for improving the truthfulness of LLMs. Now, let's get technical. Recent language models consist of an embedding layer, several stacked transformer layers, and a layer for predicting the next word. Given a sequence of tokens, the embedding layer first turns the tokens into a sequence of vectors. These vectors are then processed by each of the transformer layers in turn. We denote the output of each layer as H instead of applying the prediction layer just on the final layer. Our approach contrasts the information from the higher and lower layers to determine the probability of the next token. This idea of applying language heads directly to the hidden states of the middle layers, known as early exit, has proven to be an effective method even without special training, as the connections in transformer layers allow the hidden representations to evolve gradually without abrupt changes. We then compute the probability of the next token by contrasting the output distributions from the premature layer, the layer with the highest distance from the final layer, and the mature layer, the final layer. The motivation for selecting the layer with the highest distance as the premature layer is to maximize the difference between the mature and premature layers. Section Summary. Large language models, LLMs, have the potential to generate content that deviates from real-world facts, which is a challenge for high-stakes applications. To address this, we propose a decoding method called decoding by contrasting layers, DoLa, which emphasizes factual knowledge from higher layers and downplays lower or intermediate layer knowledge. Experimental results show that DoLa improves the truthfulness and factual reasoning of LLMs without the need for external knowledge or additional fine-tuning, making it a practical and efficient strategy for improving LLM performance. Section 2.1 Factual knowledge evolves across layers. We begin by examining how factual knowledge evolves across the layers of our 32-layer Llama 7B model. We do this by calculating the Jensen-Shannon divergence, JSD, a measure of the difference between two probability distributions, between the early and final layer outputs. This helps us understand how the early outputs differ from the final ones. We notice two distinct patterns. The first pattern emerges when the model predicts important names or dates, such as Wole Soyinka or 1986. In these cases, the JSD remains high even in the higher layers, suggesting that the model continues to refine its predictions and incorporate more factual knowledge as it progresses through the layers. The second pattern is observed when the model predicts function words like was, the, to, in, or phrases copied from the input question like first Nigerian, Nobel Prize. For these simpler tokens, the JSD becomes very small midway through the layers, indicating that the model has already decided what token to generate and maintains this decision in the higher layers. This aligns with the assumptions of early exiting language models. When the next word prediction requires factual knowledge, Llama seems to adjust its predictions in the higher layers. This suggests that contrasting the layers before and after a sudden change could highlight the knowledge emerging from the higher layers and make the model rely more on its internal factual knowledge. However, this evolution of information seems to vary token by token. Therefore, our proposed method needs to accurately select the premature layer that contains plausible but less factual information, which may not always be the same early layer. We propose a dynamic premature layer selection approach to address this. To enhance the effect of contrastive decoding, the optimal premature layer should ideally be the one that is most different from the final layer outputs. We use the Jensen-Shannon divergence to measure the distance between the next word distributions obtained from two layers. The premature layer is then selected as the layer with the maximum divergence among the subset of early layers. For Llama models with varying numbers of layers, we divide the transformer layers into 2 to 4 groups based on their total number of layers, to focus on contrasting from a certain range of layers. We still use a validation set to select the best group depending on the task at hand. This dynamic layer selection strategy allows the model to choose the most appropriate premature layer depending on the complexity and difficulty of each token, thereby making better use of the knowledge learned by the different layers of the transformer model. A simpler method would be to select the premature layer by running experiments on all the possible early layers with a validation set, and pick the layer with the best validation performance. However, this method has drawbacks such as a large search space in layers and sensitivity to data distribution, thus requiring in-distribution validation sets. Our proposed dynamic layer selection strategy mitigates these drawbacks by shrinking the layer search space and making the method more robust without heavily relying on in-distribution validation sets. Once we have the premature and mature layers, we aim to amplify the output from the mature layer while downplaying the output from the premature layer. We do this by subtracting the log probabilities of the premature layer outputs from those of the mature layer. We then use this resulting distribution as the next word prediction. If the predicted probability of a token is too small in the mature layer, it is not likely to be a reasonable prediction, so we set the token probability to 0 to minimize false positives and negatives. This strategy is referred to as an adaptive plausibility constraint. Section summary. The authors conduct preliminary analysis using a 32-layer Llama 7B model to show how early exiting outputs differ from final layer outputs. They observe 2 patterns. When predicting important factual knowledge, the model continues to change its predictions in the last few layers, and when predicting easy tokens, the model keeps the output distribution almost unchanged in the higher layers. To select the most appropriate premature layer, they propose a dynamic layer selection strategy based on the Jensen-Shannon divergence. They also introduce a contrastive decoding approach to amplify the output from the mature layer while downplaying the output from the premature layer. Section. Repetition penalty. The main goal of our model, DoLa, is to emphasize real-world factual knowledge while minimizing the focus on lower-level linguistic knowledge. However, this approach might lead to the generation of grammatically incorrect paragraphs. In practice, we didn't observe this issue, but we did notice that DoLa sometimes tends to repeat previously generated sentences, particularly when generating long sequences of reasoning. To address this, we introduced a simple repetition penalty with a value of 1.2 during the decoding process. In our experiments, we focused on 2 types of tasks, multiple choice tasks and open-ended generation tasks. We used TruthfulQA in Factor, News, Wiki, for the multiple choice tasks, and TruthfulQA, evaluated by fine-tuned GPT-3, Strategy QA, and GSM-8K for the open-ended generation tasks. We also tested the GPT-4 automatic evaluation proposed by Vicuña QA benchmark to assess performance as a chatbot assistant. We tested 4 sizes of Llama models, 7B, 13B, 33B, 65B, and compared them with 3 baselines. 1. Original decoding. 2. Contrastive decoding, CD, where smaller llama models act as amateur models, while larger llama models act as expert models. And 3. Inference time intervention, ITI. ITI uses the smallest llama model and a linear classifier trained on TruthfulQA. Our experiment focused on contrasting layer differences in DoLa and model differences in CD, without additional techniques, such as limiting the context window for the premature layer or the amateur model. We set adaptive plausibility constraint, alpha, to 0.1 and repetition penalty, theta, to 1.2 as per prior studies. In dynamic premature layer selection, we divided transformer layers into groups and selected one group as candidate layers. For efficiency, only even-numbered layers were considered as candidates. This design limits the hyperparameter search space, requiring only 2 to 4 validation runs. We used either two-fold validation or a specific validation set to select the optimal group. For Vicuña QA, which lacks a validation set, we used the best group from the GSM-8K set. In the TruthfulQA multiple choice task, we used the default QA prompt. In the adaptive plausibility constraint, we replaced negative infinity with -1000 to avoid ruining language likelihood scores. Repetition penalty is unnecessary for likelihood score calculation. We used two-fold validation to identify the best group of candidate layers based on MC3 score. Results showed significant performance improvement for llama models in 4 sizes, outperforming ITI and CD and confirming the effectiveness of our method. The higher layers were consistently chosen in two-fold validation. In the factor multiple choice task, each example has a long paragraph and 4 full sentence options, with 1 being correct. We used its news and wiki subsets as the two folds for two-fold validation. We used -1000 instead of negative infinity for the adaptive plausibility constraint. Our method generally outperformed baselines by 2 to 4% and was more effective than CD, except in the 13B model on the wiki subset. The chosen candidate layers were consistently lower for factor. This differs from TruthfulQA, which selects higher layers. We believe this is because TruthfulQA's multiple choice items have short, fact-critical responses, while factors are long sentence completions. As noted, contrasting with higher layers works better for key facts, but for sentences with lots of easy-to-predict tokens, lower layers may be more suitable. Section summary. The DoLa model aims to prioritize real-world factual knowledge over linguistic knowledge, but this can lead to the generation of grammatically incorrect paragraphs. To address this, a repetition penalty is introduced during decoding to reduce the tendency of the model to repeat previously generated sentences. Experimental results show that the DoLa model, with the repetition penalty, outperforms baselines in tasks involving multiple choices and open-ended generation, demonstrating the effectiveness of the approach. Section 3.4.1 TruthfulQA. In this section, we'll discuss 2 main topics, TruthfulQA and chain of thought reasoning. We'll also touch on our automatic evaluation with GPT-4 and the comparison between static and dynamic premature layer selection. Firstly, let's talk about TruthfulQA. In this open-ended setting, we use 2 fine-tuned versions of the GPT-3 model to judge the truthfulness and informativeness of responses. It's easy to achieve a perfect truthfulness score by not providing an answer, but this results in a 0 score for informativeness. In our experiment, we found that using higher candidate layers for decoding improved the truthfulness scores while keeping informativeness above 90%. Our method also kept the refusal to answer rate under 10%. Overall, our method improved the combined truthfulness and informativeness scores by 12% to 17% across 4 llama models, matching the performance of ITI, which uses supervised training with human labels. Next, we evaluated our decoding strategy on tasks that require chain of thought, COT, reasoning ability. We tested our method on strategy QA and GSM-8K, tasks that require not just factual accuracy but also logical reasoning. Our results suggest that contrasting with lower layers is effective for reasoning tasks. In strategy QA, our method improved accuracy by 1 to 4% across 4 llama sizes. In GSM-8K, a math word problem benchmark, our method improved accuracy by 2% for most llama sizes. We also evaluated our decoding method on the FactualQA benchmark, which uses GPT-4 for automatic evaluation. Our method notably outperformed the baseline, especially in the 13B and 33B models, indicating its effectiveness in open-ended chatbot scenarios. Lastly, we compared static and dynamic premature layer selection. We introduced a variant of our method, DoLa static, which selects a constant layer for contrasting throughout the decoding process. While DoLa static performed better by contrasting lower layers, it was less versatile without a task-specific validation set. In contrast, our original method, DoLa, maintained high scores in both subsets, almost matching the best-performing DoLa static layers, highlighting its robustness. Furthermore, DoLa simplifies the hyperparameter search space, requiring only 2 to 4 bucket tests, almost 10 times fewer than the 16 to 40 runs needed for DoLa static. Section Summary. In the open-ended TruthfulQA setting, ratings are determined by 2 fine-tuned GPT-3 models based on truthfulness and informativeness. Our method consistently improves truthfulness scores, maintains informativeness above 90%, and has a low refusal-to-answer rate. We also evaluated our decoding strategy on tasks requiring chain-of-thought reasoning and found that contrasting within lower layers is effective for achieving good performance. Section 4.2 Random Layer Selection Baseline. In this section, we'll discuss various aspects of our proposed method, DoLa, and its performance in comparison to other models. Firstly, we wanted to understand how effective our dynamic layer selection method is. To do this, we compared it to a baseline method where layers are chosen randomly. The results showed that our method outperforms the random approach, emphasizing the importance of our strategy based on Jensen-Shannon divergence, JSD. We also noticed that DoLa sometimes repeats content, especially in Strategy QA and GSM-8K. To address this, we introduced a repetition penalty. This improved DoLa's performance on Strategy QA, but it negatively affected the baseline's performance. For CD, the penalty offered slight improvements but was still less effective than the baseline. We also wanted to see if DoLa could be applied to models outside the llama family. We tested it on the MPT-7B model and found that it improved performance on most datasets, except for GSM-8K. This suggests that DoLa has the potential to be used across various transformer models. The exception with GSM-8K is likely due to MPT-7B's limited math capabilities. We conducted a qualitative study using TruthfulQA examples answered by Llama 33B both with and without DoLa. The answers were evaluated for truthfulness and informativeness by a fine-tuned GPT-3. The results showed that DoLa was more effective in avoiding the generation of false information. We also evaluated the impact of DoLa on decoding latency and found that it increases the decoding time by a factor ranging from 1.01 to 1.08. This slight increase suggests that our method can be applied widely with minimal increase in cost. We then discussed the issue of hallucinations in LLMs, which refers to content generated that is not based on training data or facts. Various strategies have been used to mitigate this, including reinforcement learning from human feedback, distillation into smaller models, inference time self-consistency checks, multi-agent debating, and inference time intervention using human labels. We also discussed the distribution of linguistic knowledge across transformer layers. Research has shown that BERT behaves similarly to classical NLP pipelines, with early layers managing syntax and later ones handling semantics. This distribution can change based on pre-training objectives and tasks. A similar concept to ours is contrastive decoding, CD, which aims to enhance fluency and coherence by contrasting expert and amateur language models. Unlike CD, our DoLa method dynamically selects early layers for less factual predictions based on token difficulty. This adaptability allows our model to cater to token and context complexity. Finally, we acknowledged some limitations of our DoLa method. While it enhances factuality in LLMs, we have not explored how it would perform in other dimensions such as instruction following or learning from human feedback. We also rely on existing architecture and pre-trained parameters, not using human labels or factual knowledge bases for fine-tuning. Our method also does not use external retrieval modules like some retrieval-augmented LLMs do, so it cannot correct misinformation acquired during training. Despite these limitations, our method provides a foundational improvement that could potentially be applicable to any transformer-based LLMs. Future work could address these limitations by combining our decoding strategy with other elements.